Hello everyone, our presentation is about single photon emission computed tomography and our group members are Ebru Rüveyda Üngör, Fatma Altun Kılıç and Sena Bal. SPECT is one of the functional techniques of nuclear medicine. Its full name is single photon emission computerized tomography. It allows visualization of internal organs and tissues with their physiological and pathological features. It works with gamma rays. Two types of image can be obtained with SPECT: stationary and dynamic images. Stationary image is a static single image. Dynamic image is moving image which is obtained by taking one image at every fixed time and collecting all these images. SPECT is used more frequently to help to diagnose or to control cerebral disorders, cardiac problems, and bone disorders. Some of these areas are brain disorders like dementia, obstructed blood vessels, epilepsy, head injuries, and heart problems like clogged coronary arteries, reduced pumping efficiency, and bone disorders. To obtain SPECT image, a drug called radiopharmaceutical is utilized. It's injected to human body via vein, generally is found in arm, and this drug reaches the target organ or tissue. Radiopharmaceuticals does not have side effects, and its radiation spreading is at minimum level. Radiopharmaceuticals are captured by gamma cameras, which will examine the target tissue and will obtain three-dimensional images. For better localization of target tissue, it can be used with combination of computerized tomography. History of SPECT. In 1963, Cool and Edwards demonstrated single photon emission computed tomography. From 1963 to 1976, in the medical imaging area, several radiopharmaceuticals are used such as albumin aggregates, technetium-99, xenon-133, and gallium-67. In 1976, the first special head of SPECT camera is developed by Reynolds Jezjak. John Keyes developed the first general purpose of the SPECT camera. In 1983, the first successful SPECT imaging of neuroreceptor, which is in humans, is achieved by William Eckelmann and Richard Reba. In 1995, ADAC Laboratories shipped the first SPECT camera to offer coincidence detection capable of FDG PET imaging. In 2008, SPECT MRI was selected where diabetic feet using SPECT were co-registered with the patient MRI, providing anatomolecular diagnosis of the extent and location of the disease. Nuclear medicine. Nuclear medicine operates on the principle that biological substances are permeable to X and gamma rays. A radioactive tracer or radiopharmaceutical, which are called as radionuclides, can be injected to the patient in a small amount and they can be detected by radiation detectors. The production of radionuclides is decided to use in medicine in 1946 and is the most important step for nuclear medicine. There are several types of radionuclides and they are absorbed different amounts by different tissues or structures, and it causes different images to be created by gamma cameras. This is the main logic of the nuclear medicine. For example, metabolism of tumor cells are higher, so radioactive substances are absorbed more and image of these areas can be seen more bright. The history of nuclear medicine dates back to the end of the 19th century. Fundamentally, the basics of nuclear medicine are based on the presence of X-ray by Röntgen in 1895, the discoveries of uranium radioactivity in 1896 by Becquerel, the discoveries of natural radioactivity by Marie Curie in 1896. Radiopharmaceuticals. A radiopharmaceutical is a drug that can be used either for diagnostic or therapeutic purposes. It's composed of a radioisotope bound to an organic molecule. The organic molecule conveys the radioisotope to specific organs, tissues, or cells. The radioisotope is selected for its properties. Radioisotopes emitting short-range particles are used for therapy due to their power to lose all their energy over a very short distance, therefore causing a lot of local damage. This property is used for therapeutic purposes, cancer cells destruction, pain treatment in palliative care for bone cancer or arthritis. Such isotopes stay longer in the body than imaging ones. This is intentional in order to increase treatment efficiency, but this remains limited to several days. The most common therapeutic isotopes are iodide 131, yttrium-90, rhenium-188, and lutetium-177. Radioisotopes emitting penetrating gamma rays are used for diagnostic, where the radiation has to escape the body before being detected by a specific device. Typically, the radiation emitted by isotope used for imaging vanishes completely after 1 day through radioactive decay and normal body excretion. The most common isotopes for imaging are technetium-99, iodide 123, iodide 131, thallium-201, indium-111, and fluorine-18. The radioisotopes used in SPECT scanning have relatively long half-lives. For example, technetium has 6 hours, indium has 2.8 days, iodine has 30.22 hours, and thallium has 73 hours half-lives. The radionuclide technetium prepared from molybdenum by using the technetium generator and used for a variety of nuclear medicine diagnostic procedures. These technetium-based imaging agents are relatively cheap compared to PET and fMRI imaging. The problem with PET scanning is the absence of good spatial resolution. This figure is the equation of that time. The time that even means photons cannot be recorded. The capital N represents the number of scintillations, and the lowercase n measure count rates. Radiopharmaceutical used in SPECT. Thallium and technetium are the two most widely used radiopharmaceuticals in SPECT. Studies indicate that thallium and technetium are preferred more than other isotopes due to high radiation exposure in the diagnosis of some diseases. Myocardial perfusion. Myocardial perfusion scan is a nuclear medicine procedure that investigates the function of the heart muscle. This technique evaluates heart conditions such as coronary artery disease and the motion of heart chambers. The main function of the myocardium is evaluated for left ventricular ejection fraction of the heart. The scan is usually performed in conjunction with a cardiac stress test. The underlying principle of the test is that when the myocardium is under stress, the diseased ventricle receives less blood flow than the normal heart muscle. SPECT scan performed after the stress event will reveal the distribution of radiopharmaceutic and therefore the relative blood flow to the different parts of the ventricle. Technetium tetraphosphamine is a radiopharmaceutical used in nuclear medicine for cardiac imaging. Images are also obtained at rest and compared. The technetium is injected and taken up by the myocardial cells so that the initial distribution of the tracer reflects viable myocardium. Images are then taken during stress and at rest reflect myocardial perfusion and viability. Brain imaging. Brain imaging forms a central part of nuclear medicine by providing physicians functional diagnostic information about the disease status of the central nervous system. The various imaging modalities employed to study the brain include computerized tomography and functional magnetic resonance imaging. Radiopharmaceuticals used for planar imaging, single photon emission computed tomography, and positron emission tomography. In addition, two hybrids of PET-CT, SPECT-CT, and PET-MRI can be used as suitable scanning systems. Currently, SPECT and SPECT-CT imaging studies of the brain play a primary role in patient diagnosis. These brain imaging modalities involve single photon emitting agents to evaluate brain death, epilepsy, cerebrovascular disease, neuronal function, and cerebrospinal fluid dynamics.
SPECTs are actually consist of gamma camera. It is executed through gamma cameras and it's also called moving gamma cameras. Gamma camera is the equipment used to detect the distribution of radiopharmaceutical within the patient. The camera consists of several components. These are collimator, detector which consists of scintillator and photomultiplier tubes, preamplifier, positioning and summing circuit, pulse height analyzer and computer. I want to mention about how the gamma camera works. Firstly, a radiopharmaceutical is injected to the patient. It travels throughout the body and emits radiation. The process of radiopharmaceutical is tracked by a crystal in response to gamma rays. Crystals produce flash of lights. The flash comes to light sensor. The sensor converts the resulting flash of light into an electrical signal. When patient is exposed to radiation passes through the patient and comes to detector, but it doesn't do specific angle with detector in everything. Some of them comes perpendicular while other come with different angle. It cause occur in the string image and it cannot be understood. Collimator is used for prevent this situation. Collimators are comprised of thousands of holes which are put in order. Holes can be in different shapes such as triangles, circles, squares and hexagons, which is most used one. These holes provide photons traveling through the holes and the photons which come from different directions to the holes are emitted by walls between the holes. These walls are called as septa. Collimators doesn't reject scattered photons. There are 5 parameters to describe the collimators. These parameters are resolution, sensitivity, resolution at depth, field of view of the image, and septal thickness and penetration. Before I mention the parameters, I want to tell what is the scatter rejection. Sometimes a gamma photon scatter via Compton scattering in patient's body. Its direction changes and it cannot hit the detector, so it must be rejected, but collimator does not reject gamma photons which are Compton scattering. This rejection event is called as energy discrimination and done by pulse high analyzer. The first parameter is resolution. Resolution is measured by modulation transfer function, which is derivation of line spread function. The resolution of the collimator is determined from the resolution of the image is from end to end by using intrinsic resolution of the camera. In order to calculate the measured MTF at any spatial frequency, the first equation is used. The second equation is used to calculate the resolution of collimator for a single hole. The resolution depends on the width of the straight bone hole, distance between collimator surface and patient's body, the thickness of the hole, For high resolution, patients should be close to collimator. The second parameter is sensitivity. Sensitivity is evaluated by using efficiency at the surface of the collimator. The efficiency depends on the diameter of the hole and the length of the hole. The third parameter is resolution at depth. It relates with the thickness of the collimator. A change in the thickness causes variation of the resolution. Also, some acquisition problems of the data for the SPECT occur with the variation. In order to increase acquisition of the data, the head of camera is placed close to the patient as possible. The fourth parameter is field of view. The sensitivity of the image depends on the field of view of the camera. For example, in order to take an image of whole body, the rectangular field of view camera is used. The last parameter is septal thickness and penetration. Septal penetration is related with energy of the gamma, which is emitted by the source. In order to choose appropriate collimator, the energy level of the source and the condemnation of the source are great importance. Septal thickness, which is the thickness between holes of the collimator, is important for sensitivity. Collimator have some features. They are named according to their features. According to their hole direction, there are 4 collimator. These are collimator with parallel hole, collimator with diverging hole, collimator with converging hole, and collimator with pinhole. One of the features is septal thickness and length. I will mention about next slides. And there are 3 formation methods to produce collimator. These are crimped lead foil sheets, drilling into a lead block, and casting from melted lead. Collimators with parallel hole are the most used collimator types. The field of imaging is limited and the image doesn't have distortion. Collimators with parallel hole are highly sensitive and they have high resolution. They are used to image the big field compared to other collimators such as whole body. Collimator with diverging hole used to make image smaller. The sensitivity of these collimators is low. Resolution is increasing with distance because the collimators has additional components. Collimator with converging hole are used for make image bigger. When the patient is positioned close the collimator as possible, the sensitivity and resolution increase. They are used to image small organs. Collimator with pinhole operates in a manner similar to that of a box camera. This is only collimator with a single hole. They are used for very high resolution image of small organs such as thyroid to make them more bigger. We can see the illustration of collimators in left figure and some images which are results of different collimators in right figure. Septal thickness and length. Collimator has to absorb unwanted gamma rays. If gamma rays with high energy are used, septals have to be more thicker to absorb all unwanted gamma rays. In the figure, we can see the relation between gamma energy and septal thickness which is needed. For the same thickness, if the septals are longer, it creates high resolution but low sensitivity.
Second component of gamma camera is detector. It has also 2 components, which are scintillator and photomultiplier tubes. Scintillator also can be called a scintillation crystal, and it is made from sodium iodide. Gamma photons come to scintillator after passing though from collimator. These gamma photons are converted to visible light by scintillator. Many tiny flashes of light can be obtained from single gamma photon. Scintillator does this process by absorbing gamma energy and releasing them as visible photons. Quality of SPECT image increases with fraction of scintillator, and because of this situation, the dose load given the patient decreases. Before photomultiplier tubes, there is a light pipe between scintillator and photomultiplier tubes. This is fixed here with silicone grease. In figure 28, we can see that what exists inside of gamma camera. The purpose of the photomultiplier tubes is to multiply the small amount of light to a large signal. First, light photons come from scintillator and hit a photocathode which is located at the entrance of the photomultiplier tubes. Then, photocathode releases these electrons to diodes. Amount of released electrons is directly proportional with amount of light photons that hit a photocathode. The electrons are attached to the diodes, which are electrodes with positively charged. Charge of diodes are increasing along the photomultiplier tube. As a result, electrons accelerates, so they gain kinetic energy. This event serves to multiply the origin signal. At the end of photomultiplier tubes, the total electrons hit the final diode, which is anode. The produced current creates the signal that the preamplifier receives. In figure 30, we can see the event that I have just mentioned. Light photons hit the photocathode and photocathode releases electrons to diodes, then electrons accelerated by diodes, and each diode has more positively charged than previous one. Finally, in last diode, current pulse is generated and it creates signal. Then, process passes to preamplifier. Preamplifier converts the current which is produced at the last diode of photomultiplier tubes to a voltage pulse. Amplitude of this voltage pulse is directly proportional to the charge produced at the anode, and therefore the amount of light received by the photomultiplier tubes. Amount of this light is proportional to the amount of gamma photons which hit the scintillator. After all these processes, analog to digital converter converts signals. Then, position of interactions of gamma rays are determined by positioning circuit, and summing circuit produced Z signal. Positioning errors are corrected by correction circuit. There are three types of the signals come from the camera head. These are X, Y, and Z signals. While X and Y go to the computer directly, Z energy signals go to the pulsate analyzer. It counts the voltage pulse according to their amplitudes and determine upper and lower limits of acceptable energy. If the energy value is in this range, it is acceptable to generate a signal which instructs the display system to record a gamma ray as having been correctly detected at the X and Y location. The pulsate analyzer allows the spectroscopic imaging. It determines the acceptable energy range based on whether gamma rays are scattered. If gamma rays has been not scattered in patient, pulsate analyzer accepts it as good event and these gamma rays are retained. If gamma rays has been Compton scattered in patient, pulsate analyzer accepts is a bad event and these gamma rays are rejected. Spatial resolution refers to the number of pixels of the image. And spatial resolution of image depends on two things, which are spatial density of image and spatial resolution of the gamma camera. Spatial resolution of gamma camera depends on collimator spatial resolution, gamma camera intrinsic resolution, and Compton scattering contribution. For SPECT image, spatial resolution is low, because to obtain the image, radiopharmaceuticals are injected to patient with limited dosage. That means gamma camera detects limited number of photons. Also, the acceptance angle of geometry of the collimator limits the photons that can be detected. Here is the spatial resolution comparison of SPECT imaging with different imaging systems. These millimeter values represent the cell size of pixels. Larger cell size means lower resolution, and SPECT has the largest cell size. In figure 34, we can easily distinguish resolution difference between SPECT and PET imaging.
Photon attenuation, which is from a photoelectric absorption and Compton scattering, affects the quality of final reconstructed SPECT image and the quantitative accuracy. The degree of attenuation depends on two things, which are distance, that is between the source and the edge of the attenuating material, and the other, the linear attenuation coefficients, which describe the friction of a beam of gamma rays that is absorbed or scattering per unit thickness of the absorber. For example, the attenuation coefficient for the 140 kV photons from the commonly used isotope technetium 99M in water or soft tissue is 0.15 centimeter power minus 1. For the 140 kV photons, this attenuation coefficient gives rise to a half-valued layer, the thickness of material that attenuates half of the indicated photons of 4.5 cm in water. Different parts of the body have different attenuation coefficients. This can cause some image reconstructions. Scattering photons come the radiation detector. They may misguide about the origin about the radioactive source. The ratio of the scattered photons according to location 30% in brain SPECT image for 140 kiloelectron photons, 30-14 cardiac and body SPECT image for 140 kiloelectron photons. The resolution of the SPECT system is 7 mm.
Reconstruction is the process of determining three-dimensional distribution of radiopharmaceuticals which is injected to patient body. To understand main logic of reconstruction, radon transform, which is for two-dimensional distribution, can be used for explanation.